So welcome students for Nuclei in the Cosmos, and we will have the second lecture on cosmic isotopes. And let me share my screen to see slides that I distributed. Okay, in the second part, we want to talk about astronomy of cosmic isotopes and the lessons learned from observing. And our topic, our issue is to understand how the variety of cosmic isotopes came into being as we observe them in the solar abundances that are shown on this top left graph. We would like to trace cosmic forms of matter and understand the individual sources of new nuclei, which are supernovae of different types and other sources. In order to measure cosmic nuclei and solve nucleosynthesis issues, we are facing a variety of complex reaction networks that include charged particle reactions, also neutron capture reactions in a complex way in the R&S process. And the problem is that most of those sites are actually embedded, so a large mass is overlying the source of interest, and we have to rely on radiation that penetrates through this overlying mass. This is obvious for stars, but also for explosions like supernovae and kilonovae. We are facing overlying material, and we have to understand that in detail in order to properly interpret our measurements. So how do we measure nuclei in the cosmic side in the first place? There are different methods, and they complement each other, and they are summarized on this slide here. So on top you see capturing stardust, which has been discussed yesterday in the lectures. Measuring samples of cosmic rays that can be captured near Earth is a similar way of capturing material samples that do not come from the solar system directly. Then we have molecular lines and atomic lines, which are observed against background sources. So you have some background light source, like, for example, the star that releases nuclear energy, and it provides the light source that shines through the photosphere. And so you see absorption lines in the photosphere from characteristic materials. You can also have for hot stars emission lines from the material that is in the upper atmosphere of those stars. Then you can see those optical and UV emission lines as well. And finally, there are gamma rays, which are not from atomic transitions, but are from nuclear transitions in ejecta, and we try to observe these as well. So let's take a closer look at our most nearby star, the Sun. This slide shows a movie of the rotating Sun, and you see that the surface of the Sun is anything but quiet. So even a simple low-mass star like our Sun is actually not an idealized sphere that burns quietly some nuclear fuel in the core, and the surface would then simply radiate thermal energy. It's not quite as simple if we look in detail. Now for the Sun, we really do have a detailed look, which we don't have for stars that are much more distant. Now there's a long history of spectral line observations, starting with Fraunhofer, analyzing the spectra of sunlight, and you see characteristic absorption lines that are attributed to specific materials, like sodium, which has these two D lines, and there are other species that are basically in the upper photosphere, absorbing part of the light that comes from below, from the nuclear energy release of hydrogen burning. Now, this is a method that has been matured and developed over many years, and so modern instruments use spectrographs which are quite complex in design, as you see here from the example of the UV spectrograph from telescopes, with a light path that goes through many optical devices, through prisms, and disperses the light depending on the wavelength, so that you can actually make a spectral measurement from individual sources. This is a very advanced technology in the optical, and that is why we can actually benefit from a high resolving power. And in a spectrum that is shown here, typical spectrum from a star, you see many absorption lines that have different shapes and different depths, and several of those lines are actually attributed to the same elemental species. And so it is possible to deduce abundances of material in the upper atmosphere of those stars. Now for the sun, there's a history of elemental abundances from carbon to silicon that are shown here for the years starting about almost 100 years ago. And you see that the error bars, actually the uncertainties become substantially smaller, even though there are elements like nitrogen where the abundances remain at a substantial level. And so it's not easy to deduce those atmospheric abundances. One of the reasons is that the atmosphere is not quiet, as the movie showed before. And so you have to correct for Doppler motions, or you have to take into account those motions, which will actually change the line shape. So the line will be broadened from this motion, and that has to be known to precisely determine the absorption depths in each of those lines. So essentially, you need three-dimensional atmosphere models to account for this kinematics, and then you also need to account for deviations from the local thermodynamic equilibrium that underlies most of our assumptions. So with different sophistications of such analysis over the past decades, in the last 10 years or so, we have had a spectacular reduction of the C and O abundances in the solar atmosphere by 30% with respect to the widely used reference from 1998. Now, it turns out that this 30% may be a little bit too high in most recent analysis, but that's a detail. I just want to illustrate that such analyses are far from being settled. So the present-day solar abundances from photosphere analysis are shown here, and they do not show the uncertainties here, but it's interesting to look at different atmosphere models and to see how one gets practically differences depending on the details of the models that are used. Here are 3D non-LTE models compared to 1D. And it's obvious that 3D modeling and non-LTE is required for a detailed analysis for the precision like we would like to have. Now, stellar surface spectroscopy is plagued with these problems of line shapes, and this shows an example of the observed normalized fluxes in a measurement from a star different from the sun. This is an example training a library of a spectral modeling tool that is used to analyze those spectra. And on the lower level plot here, you see how only changes in the surface gravity will affect the line shape that is expected from the different elements like manganese and iron shown here. And you see that there are substantial changes that are in excess of 10% in abundance variations just from this single quantity alone. So even though you have multiple lines per species, you need this detailed spectral modeling and detailed atmospheric details in order to derive results. Then, of course, you have abundances in the photosphere, and in order to trace those back to the gas that existed when the star formed, you need to also require, you are required to model the history of that gas. That means the processing that occurred in the stellar photosphere at the time of stellar evolution or during stellar evolution of the star you are observing. Now, one of the challenges that was quite spectacular was this spectrum in the infrared from a kilonova. And you see that in the kilonova, the ejecta, they are even much more dynamic and have much larger Doppler motions than what we saw in the star. And so the same problem appears, that you have bulk velocity, which leads to blue shift or red shift, and you have large dynamics shown in the arrows here of the collision of two neutron stars and the ejection of matter as we expected from simulations. So it's a very dynamic environment, and therefore the atomic lines basically are all shifted by bulk motion, and they are broadened by the Doppler motion of these dynamic ejecta. And so you cannot expect narrow lines. And so you see that this feature here has been associated with strontium abundance in the kilonova. And you see that the feature is not a clear line that you can basically analyze by eye. This analysis is the result of detailed spectral modeling, which of course is also depending on some assumptions. So you see elemental abundances from absorption lines are not so easy to determine, and especially when it comes to dynamic environments like an explosion. One should also look at the different components of material that are ejected. And so in the dynamic ejecta versus the disk wind, for example, the abundances of heavy elements are different by orders of magnitude. So given these large differences, one has some hope that the characteristic signatures of those materials would be sufficiently offset in the spectra so that one can make a statement about abundances of, for example, actinides, as is of interest in this case. Coming back to our sun, this is the solar abundances now shown with error bars. And you see the error bars are really quite small. They are often smaller than the data points shown. And this is not the result of photospheric analysis from spectroscopy. It's actually the result of meteoritic studies. So having a sample in your hand and being able to use that in a spectrograph like shown here, where you can analyze basically in detail what is the mass of the individual components and their abundance, that is a superior source of being able to determine the abundances of materials, and especially also of isotopes. So shown here for the elemental abundances, this is the result that we are using currently. It's the best precision solar abundances from meteoritics. When you compare the meteoritic with the photospheric abundances, then you see that globally you have agreement, but you also see that some data points actually show tantalizing deviations, some even being above the 1 sigma difference. And so one could say this is an open field, and certainly it's a challenge for spectroscopy to make sure that our solar atmosphere models are calibrated and well enough understood to make those measurements. But I mentioned the advantage of having material in your hand so you can analyze it in your laboratory. And that's, of course, even more so true for the meteoritic inclusions, which are the presolar grains. And you've heard a lecture yesterday about this, so I will not dwell into details. I'm just showing here, for example, carbon versus nitrogen abundances in those presolar grains, and you see that nicely you can distinguish different groups of grains with probably different origins, and that is immediately some tracing back to nucleosynthesis sources that you can do with these samples. The open issue, of course, is how did these grains form in the first place? So what is the efficiency of grain formation, and how did they get transported to be in the meteorites in the solar system? Now, coming back to the sun, this is the solar abundance of isotopes shown here for the even and odd isotopes separately. And those results, they are inferred from the meteoritic data, calibrated to solar wind data, and supplemented by theory. So it's not so easy to have a complete sample, because in our material samples, in the meteorites, we have substantial biases. Obvious is that the noble gases are, of course, evaporated and have to be taken from solar wind data. So using those solar abundances, one can actually look how well is our chemical evolution model doing. And this is an example where the data from solar abundances have been used and confronted with a chemical evolution model for the solar prehistory, using the yields from the different supernovae over the time evolution up to 4.5 billion years ago, including all the sources as we know them today. And you see that there is a reasonable agreement between the measurements and the observations. So one has some problems in the iron group, and there are a few other interesting anomalies that one would like to look at. But this is the type of work that we can do when we have precision data from isotopes, because nuclear reactions, as I told you in the last lecture, they are always acting between isotopes and not elements. So you need isotopic data. Now let me come back to the core of the sun, where nuclear hydrogen burning is going on. Here are the PP chains shown, and they involve a few weak reactions. And these weak reactions, they lead to the co-production of neutrinos. And I mentioned the large overlying mass that is a problem, but not for neutrinos. And so in the case of the sun, we have the unique situation that we can actually measure neutrinos from the core of the sun from different neutrino processes. Here are the spectra shown for the characteristic neutrinos from beryllium, from boron, and from the other different processes that I showed on the previous slide in these different PP chains. And these neutrinos, they are emitted at different energies, and so we can use neutrino detectors to try and observe those. Neutrino detectors are massive devices. They need to be big because the neutrino interaction probability is small. So in the underground lab in the Gran Sasso, we have the Boroxino detector, which is a scintillation detector. That is a detector that measures the neutrino interaction on the spot, rather than the chemical detectors that were in use before that. It has a fiducial volume to shield against background events, so that when you have an interaction in the inner scintillator, you can trace that back to a neutrino interaction. And with the photomultipliers, you can collect the light that was deposited, and that way you can make a measurement of the energy deposits of neutrinos in this detector. And this was successful to basically measure the solar neutrino generation. Here in the case, the PP neutrinos, they were first measured. They are this red underlying shoulder, and the total measurement is what's shown in black here. So you see there's a lot of background even in the underground lab, but it was possible to separate out the component from PP neutrinos, and later on also from the CNO chain, which is quite a challenge, because the background in this region is quite structured and even higher, so that the deconvolution is certainly a challenge. So the bottom line is neutrino measurements do work for the sun. It would be fantastic to do that for all the other stars, but unfortunately you see in this result that even for the sun it's challenging. So neutrinos, yes, they are penetrating, and they are not such a promising messenger for finding out what goes on in the interior of stars. We look at the variety of astronomies that I put together here. I show the electromagnetic spectrum, basically from radio waves to gamma rays. The optical is just a small part in here. And we have basically, we can try and make measurements of isotopes across the entire range. If we want to look at radiation from the isotopes directly, then this is a nuclear spectroscopy, and that requires that you measure gamma rays. The typical energies are the energies that we discussed earlier this morning. It's the binding energy of the nucleons, so you talk MeVs. The energy level differences are MeV type. So this would be the direct observation, but I mentioned already several indirect observations that we can see. We can look at hot plasma, for example, in X-rays. We can look at cold gas in the infrared and molecules in radio. And then the problem is to try and relate those atoms and molecules to newly produced nuclei, which is not so easy. And this is why I added to this astronomy here Presolar dust and astroseismology and gravity waves as one part, and cosmic rays and neutrinos as another part. So if you measure in non-electromagnetic messengers, then you can use that information and complement it with the methods shown here. But let's go back to radiation. When you look at normal radiation and you want to detect it with some kind of detector, then typically this is the interaction of the photoelectric effect that dominates at low energies. So at energies in the optical and up to X-ray ranges, practically the photoelectric effect is the effect that makes the energy deposit inside your detector from a photon that you measure from a cosmic source. And as the energy goes up, things become a little more complicated, because the energy of the photon then is comparable to the binding energy of the electrons in the atomic shell, or even the electron appears to be free. And so Compton scattering becomes important, and that's the red line shown here. And Compton scattering means that the energy is not locally deposited, but you are generating a scattered electron that then may produce Bremsstrahlung and all kinds of other stuff. So you have secondary particles, and your energy deposit is not locally in the volume anymore. You need bigger detectors, and you need to capture all the energy to make a bolometric measurement. At even higher energies, pair creation becomes important, and pair creation sets in above an energy of something like 1 MeV, and it becomes dominant interaction at say GeV energies, which is shown here. So all the telescopes that measure energies above say 100 MeV or so, they are basically tracking chambers that measure the pairs that are created by pair creation in your detector. So these are the basic principles of physics that goes on inside a detector. And I should also mention that for radiation up to X-rays, you can actually do light collection. So you capture light from a larger aperture and you focus that on your detector. You can do that because materials will be reflecting, but this reflection stops basically at energies of about 100 keV, because the wavelength of the radiation is then in the same order of magnitude of the separation of the atoms. And so you can imagine that the light basically falls through the cracks between the atoms. And so light collection doesn't work for gamma rays. And that's one of the difficulties that these high energy telescopes are facing. At the moment, we still have 2 missions operating that measure gamma rays from cosmic isotopes. This is the Integral spacecraft from the European Space Agency that is in a highly eccentric orbit, and it was launched in 2002, and it will enter the atmosphere again in 2029. So it still has a few years to operate, and luckily all the components work till today. Remember, this was planned only as a 3-year mission, and it's now in its 19th year. So the other observatory is NuSTAR. It is mentioned here because it also can observe nuclear radiation, because it has highly reflective mirrors that operate up to energies of 80 keV. And there you can actually make imaging, and 80 keV is the energy where a few nuclear transitions also occur. So those are the two spacecraft that are in operation, and you see these telescopes have to be operated in space because the atmosphere is not transparent to those high energy X and gamma rays. The basic principles for telescopes in MeV energy range are indicated here. You can have a very simple, basically a pinhole camera or a collection instrument that basically only defines an aperture and collects radiation in a detector that can be a scintillation detector. And this was the first generation of detectors that was flown in the 1970s and 1980s. Then this is a refinement of the same principle where you have a detector that is separated in different pixels, in different detection elements. Remember, they have to be large because you have secondary particles, so you cannot work with micron-sized pixels anymore. You have to have detectors that have dimensions, pixel dimensions of on the order of a few centimeters. And then you can put something like an occulting mask with some openings in your aperture, and that gives you imaging information of a much better quality than what you have seen up here. And I think the ideal instrument is actually a Compton telescope, which does not block a part of the radiation because it's precious to measure those photons, because you only have small detectors and you cannot do light collection. So measuring each photon through a coincidence technique and using the physics of Compton scattering to try and make sense of the different measured parameters here, that is a complicated telescope. It's also called Compton telescope with this coincidence setup. And I think these are the most sensitive instruments that can be built for MEV radiation. So the imaging principles for those different detectors are shown here. For the Compton telescope that I just mentioned, when you have a photon coming in, then that photon can scatter by some angle in a thin first detector, and the scattered photon is then absorbed. And you can have another photon coming in that scatters by the same angle, but it comes from a different direction. And if you have several photons coming in from the same source, then you would measure basically different such scatterings. And in this case, 3 such scatterings are shown from the same source direction. They have very different scattering parameters, but their origin can be attributed to the same source. And that is the way how Compton telescope data have to be analyzed. So in the measurement itself, it looks a bit confusing, but you have to basically do a forward folding or a back deconvolution to try and analyze those data. With the coded mask, it's much more straightforward because you can distinguish different source directions on the sky by looking at which of your pixel detectors is actually seeing the source through the holes of the coded mask and which is not seeing the source. And so you have a coding in your measured counts in each of the detectors that reflects the mass and the brightness distribution on the sky with the different sources. To show you one of these instruments in full size, this is a sketch of the Compton telescope that was flown on the Compton Gamma Ray Observatory of NASA. That was flown in 1991 to the year 2000. And it's a massive instrument that weighs several tons. It's about 2 meters tall, and it has a number of scintillation detectors with photomultiplier detectors for the first and second layers. This is scintillation with sodium iodide, and this is a liquid scintillator. And here is the principle shown again, what the Compton formula used to translate the energy deposits and the positions measured in these 2 interactions to construct an arrival direction on the sky that in the ideal case will overlap from many such measured events to show you where the source is. The coded mask telescope that we will be talking a little more about is the Spee instrument that I have been working with over the last 20 years. It has a coded mask shown here, and it has a germanium camera shown down here. This is a picture of the germanium camera with 19 germanium detectors. They are of hexagonal shape, and they are densely packed, as you see, and each of them is probably the size of a Coca-Cola can or something like that. So the coated mask is shown here. It's made of tungsten, and it is made to match the geometry of the camera in this way, and with this complex pattern, you achieve a maximum coding for the different directions on the sky. So it looks complicated, but this is basically a mathematical procedure to find out how you have to place your openings and your closures of the coded mask to get maximum information about the sky. And this instrument with the germanium detectors has a superior, very high spectral resolution, so it can be used for spectroscopy very nicely. And the germanium detectors, they are shown here, they have a fairly homogeneous electric field inside, so that when you have an interaction here, you are collecting basically the charges that are generated by the energy deposit in the semiconductor in the germanium crystal. And this is the anode that collects the charges. And this is a detector that had been used already at the Almaty-Hesse Solar Observatory, and it's also used in the spectrometer of Integral. A typical spectra of a germanium detector will be familiar to many of you. This is how they typically look like. So this is a measurement from typically a few days of observation with Integral, with the spectrometer. And it's characterized, the spectrum is characterized by a continuum that falls off towards high energies. And there are many lines superimposed on it. In fact, close to 400 different lines. And all those lines can be attributed to some kind of material that is activated by cosmic rays as they hit the spacecraft and instrument. So all of those lines are actually instrumental as you see them. And that means if you want to analyze something from the skies for celestial radiation, then you have to understand this background to a very high precision, better than 1%, in order to be able to distinguish contributions, additional contributions that may come from additional counts from the sky. So the count rate of celestial photons is many hertz, so many per second. And typically from cosmic sources, you get maybe a photon every few hours. So that tells you that background has to be well determined, and you have to know in detail the response of your instrument. On top of that, the cosmic irradiation of the detectors, they destroy actually the charge collection in the germanium detectors. And so you see here the spectral resolution as measured in some of these instrumental lines. It always is degrading over a few months until we restore it again by annealings, that is by heating the detectors for about 2 weeks to 100 degrees centigrade, and then cooling them down again to the operational temperature of 80 Kelvin. So this annealing basically is shown here in its profile. It raises the temperature for a few weeks, and then it goes down again after a couple of weeks. Now, such an instrument is also not easy to analyze, but essentially what we are looking for is the characteristic signatures from celestial sources in the different detectors. We have 19 detectors, and these are detectors from 0 to 19 shown. And you see that in the case for this example here of a bismuth line, you see that the inner detectors, the ones in the center here, they are shielded from the outer irradiation source, and that's why they are counting fewer counts in bismuth that comes from the anticoincidence that surrounds the instrument. And in this case, you see germanium. This is a background line from germanium that is higher in intensity in the inner detectors because those are surrounded by germanium detectors all around. The outer detectors not. And so you see nicely you have characteristic signatures from the background. You also have characteristic signatures from the coded masks that are shown here. And the data analysis basically has to determine in each spectral bin, and for each detector, the number of counts that you see from the sky, which is the intensity of the sky folded with the coded mask response matrix. This is the background, which is determined from background modeling. So analysis is not straightforward, and it actually needs a model of the sky intensity that is iteratively improved until you have a good match, and then you can talk about detecting sources. So not at all straightforward, but it works, as you can see here. In the case of the celestial aluminum line that is shown here, this is the line that comes from the sky. These are the error bars that you see here. You see it's a very significant measurement. The line shape is actually known to be broader than instrumental resolution. And you can see here in light gray a background spectrum that is suppressed by a factor of 5, and that has also a broad background line in the vicinity of this aluminum line. But you see from the line shapes that there is a clear distinction between what comes from the sky and what comes from the instrument. And also these two strong instrumental background lines, they are fully suppressed. So even though it looks complicated, it actually works. Also for the cases of other energies, like shown here for the titanium line and here for nickel lines. And I will discuss some more of that a little later. So with those gamma ray telescopes, we can see cosmic isotopes directly. We can, however, see only the ones that have a rather rapid decay time, so that they are bright sources from the minute amounts of material that will be ejected. And here is the table of different isotopes. The most short-lived one that we are expecting to see is beryllium-7 from Novi. Nickel-56 has been seen with a half-life of about 9 days, and then the half-lives extend up to iron-60, which has a half-life or a mean decay time of 3.5 million years. So basically, from a few months to 1 million years, we can measure different radioisotopes and see what we can do with it. So you see the candidate sources are mentioned here, and I will go through some of those examples. Now, there are other methods to determine abundances of cosmic isotopes, and I don't have time to go through each of those in detail, but let me just list them. So I mentioned already the laboratory instruments, and when you have terrestrial sediments, then you may look for cosmic material that actually was forming a sediment on terrestrial surfaces or on lunar samples, and we will see some examples of that. Then you can fly instruments, those laboratory instruments, in near-Earth space, and they can capture cosmic rays and make an in situ analysis of the material that is coming in cosmic rays. And of course, meteorites and their stardust inclusions can be analyzed. But this is all material analysis with laboratory instruments. Then X-ray emission from young supernova remnants shows hot plasma emission, and from hot plasma you get only X-rays, but hot plasma is related to nucleosynthesis sources, so we will also see examples of this being discussed. And finally, there's radio emission from molecules containing specific isotopes, and some of those contain even radioisotopes. You may be familiar with the carbon isotopes that can be seen in the CO molecule. That would be carbon-12 and carbon-13. And radio emission also has been seen from a molecule that contains radioactive aluminum-26. So I will probably mention that in an aside from the scientific discussions that I now want to go into. So a few examples only, because I don't have so much time to discuss all the aspects that we have learned. But let me start with understanding the sources of nuclei. So let's look at individual stars, supernovae of the core collapse type or supernovae of the type 1a type, and see if we can make measurements there. So our prominent example of a core collapse supernova is supernova 1987A. The supernova occurred in 1987, as the name said, and at the time one knew that a star that was known from catalogs before has brightened up, and finally, after the case was not there anymore. So the star disappeared, and then neutrino detectors have seen a few counts in different neutrino detectors here. So even neutrino measurements were possible from the supernova as the core collapse formed a neutron star and neutralizes the matter. So many neutrinos were generated. And also, gamma rays have been successful in seeing the traces of the two expected lines from Cobalt 56 decay here, which are at 850 and 1.24 MeV. And these are the two lines that are expected, and they have been seen by the Solar Maximum mission, which was not at all aimed at this. And there were follow-up observations that confirmed the existence of those gamma rays. But it was actually surprising to see that as early as in August, so half a year after the supernova exploded, because of the large overlying atmosphere. And this large overlying atmosphere is radioactively heated from the inside with the radioisotopes that are shown here, and the bolometric light that you can measure from the total envelope of the supernova reflects the degrading intensity of this radioactive heating inside. So this is measurements in bolometric light with optical and infrared detectors. So supernova 87A is already a multi-messenger demonstration of what you can do when you want to look for cosmic explosions and what they create. Now, we were even more lucky with New-Star telescope, because New-Star actually observed those two lines from the radioisotope titanium-44, which I mentioned before. This is responsible for the long-term energy deposit in the late light curve after 10 years or so, when all the short-lived radioactivities are decayed. And so from the bolometric light curve measurements, one already had an idea of how much titanium you saw. And it was brilliant that the hard X-ray detector of the New-Star telescope actually could measure that. And so we have now direct witness that supernova 87A actually indeed created this isotope that is radioactive with a time scale of about 90 years for decay. So measuring supernovae is promising, as we have seen in this case. And let me show you some X-rays. This is an X-ray image made with Chandra in 3 different energies. So it shows the characteristic emission from oxygen, silicon, and iron. And X-ray spectroscopy shows typical spectra like this. So this is the thermal emission of hot plasma at temperatures of millions of degrees. And it has superimposed emission lines from specific species, like in this case, a silicon line and a sulfur line and argon and the iron lines at around 6 keV energy. So making such an image with an imaging X-ray instrument, you can get an idea of where the oxygen, and silicon, and iron would be. And in this case, the puzzling image was, or the message of the image was, that you had some iron-rich knots, like out here or there, that would seem to be outside of the oxygen and silicon, and that would be kind of an inversion of what you expect, because when you expect an explosion that generates the iron in the inner part and ejects the envelope that had created some oxygen and silicon before the supernova imploded, then this is a little bit hard to understand. Now, anyway, these are very interesting emission lines, and one can look, for example, at the abundance ratios of different species and find out how much iron you typically see in such a supernova remnant. And that is done with more sophisticated analysis in advanced interpretation, where you include the ionization variations, and that allows you to separate some over-ionized material from metal-enhanced plasma. And in detail, one can see here that you can see in the iron lines, which is the graph shown here, that the type 1a explosions, they seem to show a higher luminosity on average. It's their statistical example in the iron lines compared to the core collapse events that are also expected to produce less iron. So you see that also in the plasma. But coming back to our Cassiopeia A remnant, NuSTAR was able to also measure titanium from the Cas A remnant, even though that's 350 years old. The luminosity in the radioisotope of titanium-44 was bright enough to actually show where the ejecta from the inner supernova are. And iron and titanium should actually both come from the inner supernova. One sees here, however, that the iron that is now shown in red here is far outside of where the titanium is. And that is, at first glance, a little difficult to understand, but it shows you that you have to be careful interpreting atomic spectra like from X-rays, because seeing an X-ray line or an atomic emission line requires that you have to have an electron in the shell of the atom. And when you have fully ionized material, as you can easily expect in a hot explosion, then you don't get emission from that. You only get emission when you have electrons in the shell and you have the ionization states that are compatible with the X-ray emission at around 6 keV that was seen here in those lines. So that image shows you that with radioisotopes, you can see the true location of the inner ejecta, because the radioactive emission here is independent of the ionization state and of the temperature, so of the plasma parameters of the hot gas. It actually is only due to the weak force of the radioactive decay, and so it doesn't have the bias that you have in X-rays, and one has to be careful analyzing absolute measurements in X-rays for that reason. So that was a very nice application of measuring radioisotopes directly. This remnant has been analyzed with combining it with solar observations of the abundances of calcium and iron, combining it with the brightness of the light curve as can be translated into a nickel 56 abundance. And with that, one learned basically that you need non-spherical explosions in order to reproduce that. The spherical models are those black dots here, and they don't produce the ratio of titanium-44 to an inferred nickel-56 emission that we have seen for those two objects. And so only from those two objects, we already learn that it needs asymmetry to create what we are seeing. So a non-spherically symmetric explosion seems to be rather a standard. And that uses different messengers. It uses solar abundances, it uses optical supernova brightness and gamma rays. So again, this analysis is a multi-messenger analysis. Now let me shortly come to type 1As. Type 1A supernovae are the result of the evolution of a binary system, where the binary system forms a white dwarf, maybe one or two white dwarfs, and with mass transfer, you can get the white dwarf into a critical condition. You can also have a merging of white dwarfs and to get the white dwarf in a critical condition so that it would explode through carbon burning. And that carbon burning is such a fast nuclear reaction that the white dwarf, being so compact, is basically ripped apart. And this is our standard understanding of how type 1A explosions happen. So they occur in close binary systems where at least one of the stars is degenerate. And we have used those stars practically as cosmic standard candles, because their optical light curve can be standardized. Once you scale it with the brightness evolution, then you have a very nice rise of the light curve with a peak about 20 days after the explosion, and a nice and regular fall off, at least for the first 50 or 100 days. So this nice behavior of the optical light curve makes them very useful for cosmology. And the underlying energy that is re-radiated here comes from nickel 56 decay that is illustrated here. So it's the nickel 56 decaying to cobalt 56 and later to iron 56 that generates electrons and gamma rays, which heat the ejector from inside, and the radiation transport then transports this as thermal radiation outside, and you get a maximum when the absorption for those gamma rays is maximum and the envelope is not yet leaking out those gamma rays. So the fall off comes from the leaking out of the gamma ray energy deposit in the envelope so that it cannot be captured by this envelope that serves as a calorimeter in this case. Now, you see this is indirect. This is a description of an indirect process of radiation transport. And so it was always interesting to try and measure these gamma rays directly. And this is the expected brightness evolution for the nickel lines and for the cobalt lines. And the nickel lines are some order of magnitude fainter than the cobalt lines because the supernova actually is expected to be optically thick even for gamma rays in the early time up to about 100 days. So this brightness evolution actually shows the dilution at the ejecta also for gamma rays. And for optical, that would be even later. So the nebular phase for optical is only after a few hundred days. So we had one supernova that was close enough for gamma ray telescopes so that the cobalt emission could be traced. And this is the time past explosion. And this is the cobalt line of 847 keV. That is the brightest of those two lines. And you see there are these red data points that show some brightness evolution that is not terribly convincing, but when you superimpose it to expectations from several models, then you would say, yeah, there's consistency between what we expect and what we have been seeing. Now, when you break those data points into shorter timescales of not 50 days, but rather on the order of 10 days, then you get these blue data points. They have a larger scatter, as you see here. And so you see more irregularity, but it's certainly not statistically significant because the error bars are so large. Nevertheless, from this, one could determine directly a nickel mass that is now a different determination than using the optical light. So you don't need the radiation transport. You measure the nickel brightness in gamma rays, and from that you get half a solar mass with a fairly small error. And that compares pretty well to the value that was determined with an empirical law from the bolometric light. And models typically also predict something like half a solar mass. So that was one of the successes, to be able to capture a radioisotope on the spot from a type 1a explosion. Now, the broad expansion means that these lines are broad. And so the 847 line is shown as the green data points here. And the other line coming from the same decay at 1238 keV is superimposed here as the blue data points. And there are even two different analyses by two different teams, which are nicely consistent. The error bars all overlap. And so this is clearly a Doppler broadened line emission from this supernova. And for comparison, this black line here shows the intrinsic spectral resolution of the instrument, which is the Spee spectrometer on integral here again. Now, this is the time integrated signal over about 200 days. And when we split that up into epochs, typically 25 days apart, then we have spectra that are now shown in full resolution, so not with the crude binning that is shown here, but actually with a much finer binning that should be close to the instrumental resolution. And there, when you look now for the different epochs, you have actually a problem to see the broad lines that one sees clearly in the time-integrated signal. And only when we make the binning much coarser, you can then recover broader lines again, but still you see some irregularity. And so this irregularity is statistically significant and is quite interesting because it shows that the gamma rays may come from different emission clumps that have a broader velocity distribution or maybe a bulk motion with a small broadening. And those clumps can be traced practically through the ejecta. And this is, of course, marginal analysis, but it shows interesting, tantalizing hints that maybe the spherical symmetry is also broken in these type 1a events. On top of that, in this same supernova, we actually had seen indications at about the 3 to 4 sigma level for the nickel lines. The nickel lines at 158 and 812 keV, they are not expected because this nickel should still be embedded in the envelope, but we saw something that was equivalent to 10% of the total mass, and that is surprising. And that may mean that either there is some extra transparency of the envelope in the direction that we were located at, or maybe some nickel actually sat on the surface. And that led us to illustrate that in a model that basically would have a ignition that could be triggered from accreted helium, with the helium flash quenching the white dwarf so that the central carbon ignition would be triggered by helium ignition. So that would be a kind of a double degenerate model. And so it supports the recent agreement in the community that type 1a explosions actually are a variety, and we have very different types of such events. Now, the sources of nucleosynthesis are a large inventory from the frequent supernovae that I mentioned. Then we have novae, we have jet-driven supernovae, we have hypernovae, neutron star collisions, and of course we have all the stars. And assessing all the production in isotopes of all these sources requires observations that have to have sufficient statistical precision. And this is only possible for the more frequent sources, and rare sources like the jet supernovae or the neutron star collisions, especially with their asymmetries, they will take many generations of astronomers to actually get sufficient statistics in the observations. Now, let me finally talk a little bit about how to trace the forms of cosmic matter. So flows of cosmic matter from the explosions to the next generation of stars is the question. So this is the ejection from the supernova, and then hot plasma has to cool down again to get into the next stars, where we would then see it in the stellar photospheres again as the newly ingested nuclei. This is the cycle of matter, which we would like to understand. So can we trace the forms of cosmic matter? So we are looking at the spreading of new nuclei across time and space. And in this case, this movie here shows 100 million years of 1 kiloparsec of interstellar medium. Sorry that the movie seems to be interrupting. It shows how dynamic such an environment actually is. Sorry that the movie doesn't work. You see cold gas as blue and hot gas as red, and you see the irregular shapes of all of this. So the interstellar medium actually is stirred by explosions, and it's not at all a spherically symmetric picture, and it's not clear how hot material in these red areas will be ingested into the blue star-forming material that may sit nearby, but is actually blown apart from this evolution. This is called stellar feedback, and that has been summarized in a recent paper in this sketch here, showing the radiation, then the mass and metal return, and finally the energy from the winds and from the explosions. And all of this affects the neighboring interstellar medium, and we are far from being able to generate a model for that in great detail. So here's a list of how the modeling in current simulations of galactic evolution are actually treated. And it's all full of approximations that we need to calibrate on individual examples. And so radioisotopes play a role in that. And here I list I show the production reaction networks that produce a radioisotope aluminum-26 and another radioisotope iron-60 they both have radioactive lifetimes on the order of 1,000,000 years, and so they are useful for tracing the flow of material over a few million years in cosmic space, which is a large time scale. It's much larger than how we can see supernova remnants, for example. So making measurements in those two radioisotopes traces the cosmic flow of ejecta. And this is the image that we have from the aluminum-26 sky, which shows our galaxy with a lot of emission coming from the inner galaxy, but also another massive star region in Cygnus is bright. And here is a little bit of the Orion sources, and here is Scorpius Centaurus. So the radioisotopes, they show a glow of material from those massive star regions, and that is something that we had a closer look at. So with integral, we could look into different directions in the galaxy. If this would be our galaxy looked at from the top, then you can look in different directions how the galactic rotation makes sources moving either away from us or approaching us. And that large-scale motion, which takes about 10 to the 8 years to go around one time, that motion actually produces a Doppler shift that we have been able to trace with the aluminum line shifting systematically here. So we have a velocity precision of a few 10 kilometers per second in gamma rays, which is quite impressive. And that traces ejecta that have been blown out from massive star groups. So looking at this, we could model that with a model that is illustrated here. It's basically showing stars located in spiral arms, and they take some time, a few million years to evolve, and by the time they have evolved, they preferentially are located at the leading edges of the molecular clouds that have been their parental sites, and so they are at a density gradient, so that the aluminum is basically injected with higher probability in forward directions than in backward direction, because there are asymmetric cavities formed, and so the aluminum will be moving in the forward direction for a longer time until it is stopped by the cavity wall compared to the backward direction. And this is the model that is shown with the green dots here, and it explained the graphs that we have been seeing. So this is the model. That is the green dotted line, and those are the data points that are measured. So these velocities are much faster than the velocities of the gas that we see moving in the galaxy. Now we are analyzing details of this, and I don't have time to go through each of those details, but you can see here that the cavity that is formed by massive stars and their feedback can be seen in X-ray and H1 emission with the cavity walls. And these are the stellar groups that are currently ejecting the radioisotopes. And we see the radioisotope flow towards our direction, which is the sun located here. And we can again make a comparison in multi-wavelengths to look at the cavity walls or at the parental molecular clouds or at the X-ray cavity, compare that with the gamma rays. And let me skip the details of the hot cavity, and let me just show you that on the galactic scale, we expect many such bubbles. And this is a simulation, one example of a simulation. This is another simulation that basically shows that the plane of the galaxy would be basically characterized by blowouts in the galactic halo from those massive star regions in those bubbles, in those super bubbles that form around such massive stars and clusters of massive stars. And when we summarize that, then from the Doppler velocity and from the analysis of the individual superbubbles, we obtain a picture where it's quite possible that newly produced nuclei are preferentially thrown out into the halo of our galaxy, and they might fall back sometime later into the galactic disk, so that the recycling of material also goes through a loop through the halo, and it may be less direct than what you could think of in a naive understanding of you produce some ejecta and then you see that in, for example, in European abundances in nearby stars already. It may be a little bit more complicated than that. Now, something hands-on. So this shows an ocean crust with myself and Tony Wallner on it. So this is a picture of material that comes from more than 5 kilometers depth in the Pacific Ocean. And it has been analyzed in the laboratory for non-terrestrial materials. And actually, iron-60 has been found in this material. And the iron-60 data are shown here as a function of depth, which is the age of the material. And it shows that there's a cluster of high data points about 3 million years ago. So apparently, some cosmic material containing radioactive iron-60 has been deposited on Earth and in the solar system about 3 million years ago, and a little bit maybe also around 8 million years ago. So this is very interesting measurements from the ocean crust that can be understood with nearby explosions being material of nearby explosions being advected into the solar system. And let me spare the details here. I don't have time to go through that. But this is the usefulness of a radioisotope measurement in a sediment on Earth. And here is another measurement from cosmic rays. This shows the spectrum, the mass spectrum measured with the Xrays instrument on the ACE spacecraft. That's quite an old spacecraft that operates very nicely in space. And it has measured a number of iron-60 nuclei that actually have to come from nearby cosmic sources, because iron-60 is not produced by spallation that is normally characterizing the nuclei that you see in cosmic ray materials. This is the spallation example where aluminum-26 is generated, and this shows clearly that there is material at mass 60 which must be from cosmic sources, because spallation products can only be at lower masses than iron, because the heaviest masses that you have in cosmic rays are actually iron nuclei. So when you break them apart, you get something lighter, which has been observed in many species from manganese, chlorine, aluminum, beryllium-7, beryllium-10. And so these measurements clearly show live radioactivity in cosmic rays. So we have gone now in this hour through a number of cosmic messengers, and here is the list again of all the different messengers that we can make use of to make measurements from isotopes in cosmic sites. And the summary of this is that we have a variety of different sources that produce in the time axis of, let me go back. In the time of, in cosmic times, massive stars started after the galaxy formed, and type 1a explosions added later. Neutron star mergers and rare exotic supernovae may also have happened around the same time, and the solar system formed about at a time here. And the current universe is observable, of course, in the current epoch. And all of this has to be analyzed and understood in ways to try and analyze chemical evolution, like done by Chaki Kobayashi and co-workers in this nice diagram that shows again a table of the elements with the abundance evolution of sources from core collapse supernovae, from AGB stars, and from type 1a supernovae by element. And this is a crude summary of chemical evolution modeling that, as I showed you, needs to be actually done on isotopes to be more precise. So let me flash up the summary here, which shows the status of observing cosmic nuclei. So stellar spectroscopy is certainly in an area of precision. It has very good data from optical spectra and from surveys like the Gaia survey. And so we learn a lot of that, but it also has limitations. So understanding specific sources, we use more direct observations like from gamma rays and from X-rays. And this gives us access to these explosions in better ways than going through the indirect way of old stars. The cycling of cosmic gas through sources and galaxies is actually a challenge for our understanding. And what we have learned is that large cavities here play a big role, and the source environments are different for the different sources. So, for example, neutron star mergers will have a different environment than the massive stars that are shown on this movie here. And we use different messengers that complement each other with essential diagnostics. So radioactivity provides a clock, particle measurements provide details on isotopic abundances, and there are new astronomies which contribute in their own ways. And with this, I am at the end, and thank you very much for your attention.